Viitorul e al tău, noi punem temelia. UTCP, construim pentru România. UTCP, Universitatea de Construcții București.
Thank you, Nakano-san, for the introduction. My name is Melih. I am from IHI Turkey. Today, we will try to share with you our experience, what we did. First of all, project name, seismic reinforcement project for large-scale bridge in Istanbul. Unfortunately, Turkey surrounded from north and south, North Anatolian Fault and South Anatolian Fault. Therefore, for both fault, it is sometimes hit the region. One of them, 1999, hit the Kocaeli region, very close to Istanbul. It was 7.4. According to official announcement, more than 17,000 people died and 44,000 approximately injured. More than 200,000 buildings damaged. But it was official. Actual number was much more than, unfortunately. On the other hand, in Japan also, big Hanshin earthquake center in Kobe, 1995 also occurred, and Japan experienced developing national disaster strategy after this earthquake, especially rapid restoration from damage, and then reach to adding to rescue area with that after that earthquake, earthquake. Parallel with that one, after that, our Kocaeli earthquake, 3 years later, between Japanese government and Turkish government signed loan agreement 2002, July. Then, 4 years later, as we mentioned at the beginning, the seismic reinforcement project started 2006 March. That city, Kocaeli city, very close to Istanbul. Therefore, just fault is passing only 20 kilometers south of Istanbul. Therefore, Istanbul city, for in future possible earthquake, it is a dangerous situation and a very big risk. So, in Istanbul city, divided, maybe, Bosphorus Street dividing European and Asia two parts. Between these two parts, at that time, there was two periphery roads. First periphery road and second periphery road, upper part. So, therefore, after possible earthquake, reaching to rescue area much more important. Therefore, these two periphery road, no alternative road, it should be open after earthquake. Government, because in that area, more than 200 viaduct building there are. Therefore, we have to give budget, we have to give some priority to Seismic bridge. First of all, first Bosphorus bridge, second Bosphorus bridge, Ortaköy viaduct, and Golden bridge and their approach, and Mecidiyeköy viaduct. Totally 15 bridge included to project scope as objective bridge. So immediately after starting the project, with Bosphorus University professor, with their collaboration and consultancy, they produced this two-level earthquake for response spectrum of bridge, each bridge location. First one, functional evolution earthquake, repeating period 73 years, 50 years, 50 first probability. Second one, 30 evolution earthquake, repeating period 2,475 years, 50 years 2% probability. But these apply for 14 bridges, except Mecidiyeköy Valla. We apply for Mecidiyeköy Valla because of the importance of location and strategic very congested area. Again, two level earthquake, but one of them design basis earthquake, repeating period 475 years, and second one, same as functional evolution earthquake, maximum critical earthquake. We apply for bridge. Now, mainly today we will mention improving seismicity of these structures. Two methods. One of them, seismic reinforcement. This is conventional method, we can say, in our work. Other one, base isolation. So, seismic reinforcement method, of course, very easy design and site works. Generally high cost because of foundation necessity, reinforcement necessity, and traffic restriction, traffic closing widely necessary. These are handicap of this method. Base isolation compared to conventional method, little bit complicated design and site works also complicated. Also, generally no foundation reinforcement necessity. And also, most important subject, much more less restriction causing to traffic, of course. This is especially for congested area, it is very important. The first reinforcement, as we told, conventional method, sample, Ortaköy Valla. This is coming to, before coming to first Bosphorus bridge. This is 9-span continuous PC precast concrete T girder, T-shape girder. All piers hollow core, and left and right piers is connecting outside with cabin. All bearing, elastomer bearing, except mid one, P5. Of course, in this project scope, all bearing replaced with new one, with increasing capacity, of course, and also we did RC dining. Design criteria, briefly, as I say, existing piers surrounded with new RC lining, all force, service load, and earthquake load undertake with new RC piers. Means existing pier not considered in design. Actually, of course, supported, but considered in design, considered like that. And also reaction from superstructure with new RC captive via new elastomer bearing. So one note also left bottom part you can see between existing pier and new piers we apply plastic hinge part. We separated new and old pier with foam material in plastic hinge part. Also, cabin part also we apply same thing. But between this, except this plastic hinge part, to avoid any collision of existing pier, because during a big earthquake, it can be collision and collapse to inside. Therefore, we bonded each other with special material. So you can see also that side kept in. New kept in, we installed new bearing. Existing bearing, it was sitting to half of it, PC T-shaped beam. Also, from left and right side, PC beam with cross beam together, we connected with falling down prevention cable. You can see that. So, site construction method, climbing formwork we used for our new RC lining. So, also for new cabin, we installed false board and assembly of formwork. You can see right side also. So, this was related conventional method. Now, we will briefly explain base isolation for Mecidiyköy. Mecidiyköy, it is a very congested area in Istanbul. Upper and low parts, it was very heavy traffic, 860 meters length approximately. So existing structure also superstructure and pier C30 concrete plus and footing C25. Of course, we are this is important for us because while making new pier, we are not apart from existing one. We are selecting class also very close to this material. So existing structure, 25 axis double piers. Each double piers longitudinal direction, superstructure and substructure hinge connection. Single piers, you can see the bottom, only 3 piers, single impost. Superstructure, substructure, connected rigid connection. It was like that. And also, when we check the existing structure, because it was designed and constructed approximately 50 years ago, therefore, at that time only thermal force and service load considered. Earthquake also considered, but very few coefficient factor, unfortunately. Therefore, when we check the crack, pier crack occurrence capacity, seismic coefficient, it is very low, 0.5, 0.10. Yield point also you can see. And footing stability also approximately 0.20. So, during analyze, in longitudinal direction, when we check 0.7 period we obtain, when we check to this 0.7 period, it comes to in longitudinal direction in big earthquake, maximum critical earthquake, approximately 0.6 acceleration is obtaining. Therefore, if you consider footing capacity stability approximately 0.20, it is very far, of course. What we selected base isolation for Mecidiyköy weather, the original situation of under bridge traffic approximately 9 line there was. if we follow conventional method, of course, RC lining we have to do. Also, foot also should be enlarged. Then almost 3 lane will remain. We have to close the road 5 lanes, 4 lanes, something else. This is not acceptable for general direct highway. Actually, before we start this project, seismic reinforcement project, one Turkish local company, it was designed like that. After we made contract, we suggested this way, base isolation. With that way, we closed only from left and right side, only one lane closed to traffic. It was very good study. Mainly, briefly, I will explain Mecidiyeköy piers. It is a hexagon full concrete structure. For shear capacity increasing, we did steel jacketing, but to do this steel jacketing between steel jacket and existing pier, we injected non-shrinkage water to get integrity between old and new. And also, we installed LRB bearing, rubber bearing. This is main part of course. And also, RC lining, foot protection in bottom part. This is also enlarging bending capacity also. And RV bearing, net rubber bearing, you can see, so structure it is very, compared to original one, little bit different. 27 rubber and 16 steels. In 4 corners, there are 4 lead parts. Of course, all LRB bearing tested with service road, all product, but 2 of them randomly selected and then sent to California laboratory, California University laboratory for under earthquake load, according to ASHTO, in many combination. We did tested. So, characteristic behavior of base isolation, you can see also. Subject, it is absorbing all deep in superstructure as much as possible, less force transfer to foundation. Now also, this test group also you can see shear forces 1000 around displacement also you can see. So sequence, briefly I will explain. First of all, to integrity of existing and new steel jacket. First of all, we did chipping on pier, then excavate around pier column, very limited as we say, and install steel jacket, then protection foot. This is what we apply plastic each location. Then we construct also concrete band pipe in 4 corners of piers. Then backfilling and compacting with it. And install steel band, as you see. this is of course to install new LRB bearing, we have to transfer this steel band, of course. We installed in four corner flat jack, each one 400 ton approximately. Jack superstructure up. With this way, we carry with this steel band or coming force. Then cut gear up in two stage. You can see also. After that, bottom part of LRB, we install rebar. After rebar installation, also last part of steel jacket we apply. Then LRB base plate installed to location. Pouring concrete below of base plate, LRB base plate. Then entering on superstructure LRB bearing. Then install LRB bearing. The bottom part 6 and 24 volt. It was at the beginning designed also, upper part also, it was same, but because of difficulty, we converted, because superstructure is moving, to matching, it is not easy subject. Therefore, we converted that one to welding, upper part weld, down part with both connection. Then, most important subject, of course, after this LRB baking, the upper part, concrete nulture cage bolted injection, because you have to be sure 100% you have to, of course, this is self-leveling, but you have to reach every part, otherwise continuity can be problem. Also, mock-up test we did in separately from that one to achieve. Then jack superstructure down after putting concrete and then getting strength, of course. Then removing steel band. This is final shape of after painting. The part, upper part, black part, you can see with color. This is reason in USA, in one bridge, after burning one car, burn also LRB bearing, then collapse the deck part. Therefore, they strongly suggest us to cover with steel sheet, avoid any fire in case. This is sequence also, you can see, this is repeating what we explained before, foot protection, steel band, and steel jack-up, cutting, LRB bearing installation, then last part apply and back clean, and then this is finished part. So this is also a simple compression table to give idea. Here it is 3 viaduct, which in our project scope, alternative viaduct, 408, 409, 411, and HDQ viaduct, which was done with base isolation. So you can see this is not 100%, but for 408, 2 billion Japanese yen, 409, 1.2 billion, you can see prices. And also length, area, and pier numbers, total pier numbers. So unit price for each is 132 million, 92 million, 96 million, but electric provider 38 million. Ve huge difference between exaggeration and conventional method. And also, if you put the square meter, also there is difference, as you see, sometimes 2 times of cost. Thank you very much for your attention.
Hello everyone, Brazil. My name is YANAGI from IHI Infrastructure Systems from Japan. So the schedule is already over, but it would be appreciated if I got your attention for another 5 or 10 minutes. So in my presentation, I will focus just bridge maintenance and management. The title is Development Activity for Bridge Management Support System in Vietnam. IHI is IHI is working to realize the preventive maintenance of infrastructure, especially road bridges, in developing country with using digital tools. In Vietnam, we are researching and demonstrating the feasibility of introducing the bridge management support system. The name BMSS developed by IHI Group. In order to participate in the bridge maintenance and the management business, the business model is promoted with the local partners in Vietnam. This is the contents of my presentation. The first, market and issues for bridge maintenance in Vietnam. Second, what is BMSS? And third, introduction about activities in Vietnam. And finally, the next actions for our activities. Here is the market and issues bridge maintenance in Vietnam. IHI is cooperating with a consultant company named Deloitte Thomas to investigate the market and issue in Vietnam for bridge markets. Please focus the graph. The number of bridges built in Vietnam has rapidly increased from 1990 and has peaked to 20,000. It means around 20 or 30 years ago. And the total number of bridges is estimated to be around 32,000 in Vietnam on 2023. Therefore, it is estimated that bridge maintenance will become a serious issue in Vietnam. Here are the challenges for bridge maintenance. Generally speaking, the budget and the manpower is limited for bridge maintenance. So to solve this challenge, here I will focus on 2 important matters. First, it is important to store and visualize the maintenance data, especially, for example, the history of inspection and repair works, and the bridge service level. The service level means a kind of structural healthiness level of structure. The effective order for bridge inspection and repair works can be decided by storing and visualizing these data. The second matter is it is important to realize the preventive maintenance. The preventive maintenance are to ensure safety and ensure stable logistics. By ensuring safety, we can avoid the sudden collapse and accident due to degradation or earthquakes. and, and, and we can avoid the economical damage due to road closure or traffic disruptions. So IHI developed a bridge management support system to realize these matters. So here I will show what is BMSS. BMSS is Bridge Management Support System developed by IHI. This system has the function as database, for example, bridge specifications or inspection data and any repair works results and so on, as well as has the practical analytic function also. So, as mentioned on the presentation by Mr. Shibata, in Japan, periodic inspection for road bridge has become mandatory from 2014. The BMSS has been invested to support the bridge maintenance and management to increase the workforce efficiency for local government. For example, support to organize the bridge specifications, the history of inspection, and repair works, and so on, and to support to estimate the approximate cost for repair repair works, and support to make and update the long life repair plan for road bridges. As I showed the previous slide, IHI is working to realize the preventive maintenance of infrastructure in developing countries. But I'd like to show the activities in Vietnam to develop our systems. And now, IHI cooperates with 3 local governments in Vietnam: Hai City, Da Nang City, and Ho Chi Minh City. These 3 cities are very big cities in Vietnam. And IHI is cooperating with one private company in Da Nang City. This company's business is to operate and maintain the road asset. So here is the case introduction with local government in Hai City. First, IHI we introduced for BMSS system and proposed BMSS trial. The trial means that firstly IHI selected 10 bridges in Hai City and input the bridge data in our systems and makes the output and prepare the document and demonstrate how to use our systems. This trial is free because this is trial basis. To collect and input the bridge data for these 10 bridges, we carried out the site survey by ourselves in Hai City. This is the photo, the site survey. By using the input data, IHI prepare the output and submit the outcomes to Hai City's government. And if they want to use our system by themselves, we provide the system account to them and how to instruct how to use our systems as trial basis. Not only the demonstration on site, IHI studied the applicability of BMSS itself in Vietnam. This is the table for comparison. This is the comparison table for the specifications for bridge inspection between Vietnam and Japan. By comparing the specifications, we concluded that the concept of BMSS in Japan can be applied in Vietnam. So for example, the frequency of periodic inspection is basically once every 5 years. And inspection method is mainly close visual check. But if necessary, some appropriate equipment should be applied. The evaluation of standards level is 4 levels. And the inspection record and any technical data should be kept during the period service or bridges. This is the final slide showing the next action for our activities. There are 2 ideas. The first one, we need to study for better standard to update the BMSS system developed in Japan. Because our system has been developed in accordance with Japanese standard. So we need to develop updated, for example, unit cost for repair works and evaluation concept for structural healthiness level, vitamin soundness level, and estimation method of degradation curve for bridges. The second item is we need to spread this importance of preventive maintenance. So, as I shown in the first slide, the budget is limited for bridge inspection as a bridge maintenance. So, in order to secure the budget for bridge maintenance, it is necessary to make government agencies understand the importance of the preventive maintenance. That's all for my presentation. Thank you for that.
Viitorul e al tău, noi punem temelia.